So I'll tell you a couple of things today, some of which are true, some of which are useful. And I think the intersections of those two are the null set. It's okay to take some pictures. I'll have some links and links to GUIs and papers, so I think that's fine. Apparently it's also okay to launch grenades. I don't know about that camera. So we work in three broad areas in the lab, one of which has to do with sort of stochastic Navier-Stokes. So there we're very interested in sort of the efficiency of transport of vesicles, accounting for hydrodynamic fluctuations. We also work on bacterial predator-prey dynamics, in other words, how bacterial predators go about finding their prey. And I would say that 70% of the lab is focused on inference in vivo, in other words, learning models from imaging data. So what is the grand plan? The grand plan is really to start off with single photon arrivals, that is, data acquisition at the fastest possible available timescale for at least optical data, at the single molecule level, sort of crunch through math, and ultimately arrive at a picture of life at a spatiotemporal scale that is not otherwise available by other methods. And to sort of help motivate this problem, I would say that we confront one fundamental problem in single molecule biophysics, or I would argue in biophysics perhaps even in general, and that is the model selection problem. The data is complex. Single molecules themselves are rattled by thermal fluctuations. Measurements add incredible noise. And so it's deeply uncertain what model is responsible for the data as we see it. So for example, on my right-hand side here, what I show is sort of a picture, a single frame of some kind of tracking movie where it's unclear whether you have one molecule diffusing or potentially very many other molecules present in that frame. In the one in the middle, I'm basically showing a typical palm storm localization experiment where it's unclear what the stoichiometry of the complexes pointed out by green arrows are. And in the last one on my left, what I'm showing you is sort of a typical single molecule FRET trace, or potentially a force spectroscopy trace, where again, the number of states themselves are uncertain. So fundamentally, in each one of these methods, and I would argue in every single molecule method, we have one fundamental problem, which is the model selection problem. The bad news is that theory has been of no help so far, right? Because the more complex we make a model, the better the fit to the data. There's some caveats, and you're welcome to ask me questions about that, but I would argue in large part, experimentalists have therefore taken the brunt of the challenge and asked, how can we solve the model selection problem? And the way it's done is by fluorophore engineering, turf, structured illumination, super resolution, light sheet, PSF engineering. All these methods, I would argue, are ways of solving the fundamental problem that we all confront, which is the model selection problem. It comes at a cost. In fact, it comes at a huge cost. Each one of those have specific costs associated to them, but if I can just give the example of palm and storm, for instance, in palm, photoactivation localization microscopy, if I shine light on a sample, molecule stochastically turns on, I collect photons, I pinpoint the center of the PSF, that molecule photobleaches, right? And then I repeat the process onward and onward. That's how I get those beautiful spaghetti-shaped, crisscrossing cytoskeletal structures. Except I've compromised temporal resolution in doing it. So the experimental solution, in fact, cost me quite a bit. So if I really want to get access to life at high spatiotemporal resolution, I also need to look for theoretical solutions to the model selection problem. So what I'm arguing is that we need a better theory. We need new math. And fundamentally, what we need to do is to learn models from the data. Not just learn parameters given fixed models, but actually learn models themselves from the data. In fact, statisticians had thought about this problem, and in 1973 there was this nice paper published by a gentleman called Ferguson in the Annals of Statistics in its very first volume. The ideas here, I would say, have had a very deep impact in data science, and yet they're essentially unknown in the physical sciences. These are rigorous statistical tools that are essentially direct extensions of Bayesian logic. They turn what is a very difficult problem, which is the model selection problem for which we design a whole bunch of different experimental strategies, into a mathematical solution to the problem, which is to say, let's try to learn models in the same way that we learn parameters. If I can give an analogy to this, think about the hidden Markov model. Or at least for some of you who might be familiar with the hidden Markov model here in the Biophysical Society, what do we do when we apply HMMs to data analysis? We learn parameters, right? So measurement parameters, measurement noise, or in technical language what people call emission parameters. And we also learn transition kinetics simultaneously, because this is a joint optimization. It would be wrong to separate this as two separate steps. Right? In fact, that's what the BIC and the EIC do, is that you first learn your parameters, then you select between models. Right? So you're turning this joint optimization problem into an approximate single variable optimization. So the idea behind Bayesian nonparametrics, again, it's a formal extension of just Bayesian logic, is really to learn models and parameters simultaneously, self-consistently. Well, you probably don't want a theorist to explain to you how FCS works, but in case you've wandered in by accident from the Ocean Conference on the other side of the convention center, let me tell you in a word or two. You illuminate some small volume, molecules crisscross through it. They could be fluorescent dyes or they could be labeled proteins. Depending on, if the proteins are towards the periphery, or the labeled proteins are towards the periphery of this volume, they don't emit all that many photons. If they're in the center, they emit more of them where the light intensity is higher. So in principle, the photon arrival times themselves encode a number of things. They encode what the diffusion coefficients of those proteins are. They encode where these are located within the confocal volume. And in fact, they even encode how many molecules are responsible for the signal, as you see it. And from that, the goal is to learn diffusion coefficients and reaction rates, potentially if the molecules are reacting. Now the question is, why can't we do it? Again, that hard wall, the model selection problem that we all hit. And here it is explicitly for the example of FCS. Here's a sequence of photon arrivals. Suppose I were to analyze this using maximum likelihood, traditional maximum likelihood methods, or even Bayesian methods. If I had magically at my disposal knowledge of the fact that 4 molecules are giving rise to this signal, then I would correctly estimate the diffusion coefficient. Otherwise, I'm dead, right? I can't do it. So, what is the solution? Well, I would argue very elegantly about half a century ago, Magda and Elson proposed to collect signal for a very long period of time, autocorrelate it, right? Fit the autocorrelation function that you guys have heard of in previous talks, and from that extract dynamical parameters such as diffusion coefficients or reaction rates. And we can ask ourselves, well, what are the advantages of this? It's fast to calculate, right? It provides immediate intuition. There are many more advantages. There are serious disadvantages, one of which is it works if you have analytical forms that you can fit to your curve. It requires steady state processes, right? I mean, if you're going to collect data for a very long period of time and average it over a very long period of time, your reaction kinetics better be steady state. Requires long data sets, which therefore means that if you're doing this in vivo, you have to be careful about phototoxic damage. So I'd like to now draw an analogy to hydrodynamics. The way I see correlation functions in FCS is the way I see sort of Stokes' formula in hydrodynamics. It's not going anywhere, right? It's intuitive, it's simple to use, we can use it to explain things, but it's not sufficiently detailed for us to fly a plane. What we need is the equivalent of a computational hydrodynamics in order to be able to analyze photon traces and extract from it what is happening at the single molecule level. And when I talk about computational hydrodynamics, or in my case, these Bayesian nonparametrics, I still don't mean something that I'm running on GPU clusters, right? So most code that we write, and it's all available on my website, can be run on a single core desktop. So, how do we start from scratch? Let's start off with delta t, the time of arrival between photons. What dictates that? Well, and from that time of arrival, we wish to learn diffusion coefficients and particle trajectories, presumably. What dictates that time of arrival? Well, that's photons that arrive, or potentially camera, dark noise that contributes false signal. Now, what contributes the photons? Well, you have background, and you have the biomolecule itself, with potentially some label biophysics, some label photophysical problems. Now, in principle, from a sequence of these delta t's, I can construct a hierarchical Bayesian model and learn properties of that molecule. So far, so good, right? Now, the molecule moves. That means that there's also a diffusion coefficient dictating the motion of the molecule from one position to another. Again, I can do it. I can start off from delta t's, and I can learn diffusion coefficient. Because there's motion, I might have to use something like a Kalman filter, and in fact, probably some nonlinear Kalman filter, because there's complicated relationships, but I can do it. And here's that wall again. This is the problem that I cannot solve given 21st century mathematics as they existed up to 5 years ago. That's the model selection problem. I cannot tell you how many molecules contributed to that signal. So here's the expert slide that sort of tells you the recipe of how it is we're going to go about doing it. So basically we're going to construct the entire sort of hierarchical Bayesian framework. We say that delta t, the time of arrival between photons, is exponentially distributed, and the mean of the exponential distribution, in other words, the photon emission rate, is the sum of the background emission rate plus the emission rate of your molecules. The emission rate of each molecule is dictated by where it is located in the PSF, and a very important variable, B. That is, it's a Bernoulli random variable, it's either 1 or 0, and it dictates whether that molecule is contributing or not to the signal. And it's going to turn out to be absolutely critical. So in other words, it tells you whether the molecule is real and contributing photons, or virtual and not contributing photons. So now what we're fundamentally going to do is to turn a model selection problem into a parameter estimation problem, which is the key behind Bayesian nonparametrics. Finally, we will assume that the molecule freely diffuses in space. We don't have to do it. In principle, if my space is complicated, I would just need to either analytically or numerically solve the appropriate Fokker-Planck equation. Within the Bayesian paradigm, I have to put priors on all those things that I don't know about. And here's why I need 2 mathematics postdocs. We need to put priors on these Bernoulli random variables. These priors are called the beta-Bernoulli process, and they were roughly perfected about 5 years ago. Under different terminology or different textbooks, you might hear of them as being referred to the Indian buffet process. And we take the n go to infinity. In other words, we assume that we have an infinite number of molecules, and if they are warranted by the data, then essentially that Bernoulli random variable is flickered to a 1. Now we get the central object of interest, which is the full posterior. What we learn, or what we get from this analysis, is the probability of the diffusion coefficient, the emission rates, the positions of the molecules, and their identity as to whether they're contributing to the signal or not, given the data. And I would probably say that 90% of my lab's effort is ultimately devoted to learning ways of sampling from this posterior in order to be able to do these calculations efficiently, such that someone can just click a button on a GUI and get an answer a couple of hours later. So I don't have in this short talk, I don't have the opportunity to tell you in very great detail all of our results, but here's sort of a nugget of the results. What I'm plotting is a ground truth diffusion coefficient, which is the red dotted line. With the green dots, I'm showing our sort of estimation of the diffusion coefficient. For the parameters that we've selected, you can pretty much see that within 800 to 1,000 photons, we've pretty much converged to the correct diffusion coefficient. FCS is the blue star, and you can see that it takes a couple orders of magnitude more data for it to converge to anything reasonable. And keep in mind that the y and x-axis are in logarithmic scale, right? So it takes quite a bit longer. And of course, if you take a look at our papers, there are controls with different viscosity, laser power, dyes, labeled proteins, multi-species, different optical setups, and so forth. By the way, this is what the correlation looks like when you have 500 photons. That's what the correlation looks like when you have 3,000 photons. It's shotgun noise. There's really nothing you can fit here, right? Which is why your diffusion coefficient estimate is orders of magnitude off. So it is more computationally expensive. Bayesian nonparametrics will be, but they give you different kinds of information with, different kinds of information, especially if you're concerned about phototoxic damage. I should say that all the code is available on our website, as is the paper and all the supplementary material where all the real action lies. So, great. You've seen the example of FCS. Now the question is, can we just redo it all of it, from scratch? And I think the answer is yes. And in fact, we're trying to do it. I have either a graduate student or a postdoc on each one of these methods: FCS, FLIM, localization tracking, RNA-FISH, MERFISH, single molecule FRET, and so on. So, sort of as a summary slide, I would say that Bayesian nonparametrics are powerful logical extensions of traditional Bayesian methods. They were proposed in 1973, though the required tools that we use here, like beta Bernoulli processes, are only roughly 5 years old. I would also say that we don't give our methods name, in part because I don't feel like logic should have a name when something is an extension of existing logic. We didn't come up with Bayesian nonparametrics, we're adapting them to single molecule. I don't know if it deserves a name or not. It's also true that in biophysics, it's very hard for people to come up with acronyms that don't sound like Southeast Asian street drugs. So I'm trying to avoid that as well. Thank you. Fewer than 12 papers have been published on BNPs in biophysics within the last 3 years. 8 of those, roughly, are our own, only within the last 2 years. And I would say that BNPs suggest that math should be working hand in hand with experiments to solve the model selection problem. So far, experiments have been doing all the heavy lifting, and theorists have just been throwing their hands up in the air. Well, not completely, but in large part. So now the question is, can we work together to tackle this model selection problem? Here's a final quote: "If people do not believe that mathematics is simple, it is only because they do not realize how complicated life is." So now, oh yes, and I should say there's a couple manuscripts out there that what I talked about summarized. There's the Nature Communication from last year, PRX from this year, and a nice JCP highlights. If you want to run a GUI, that's great. We have it on our website. If you really want to learn the nuts and bolts, we are writing a textbook on data analysis that should be roughly ready in about 2 years. We have about 200 pages. We have another 200 to go, so it's going to take a short while. We do have 2 posters tomorrow at 10:30 a.m. Now, if you remember nothing from this talk, please remember this. We are recruiting, so that's the important one. Right. We're looking for an experimental postdoc. This is in collaboration with a colleague of mine, an experimental colleague of mine over at ASU, Doug Shepard, who'll be working on light sheet adaptive optics and remotely focused fluorescence imaging to unravel environmental sensing at the single molecule level. And I'm always looking for a handful of talented theory postdocs who are willing to undertake many of these challenges, sort of one method at a time. And no talk would be complete without the acknowledgments. So number one, thank you, Michelle, for putting me here. Thank you, Liz, for moderating. Thank you, all those of you who are here in attendance. I know it's extremely late. It's like past 9 p.m. right now. And the people who did all the work. Ioannis Kouralis, who's off to a very nice faculty position. Sina Jazani, who's wrapping up a bunch of hopefully high-impact papers and moving on to great things. And Maysam right now, who's also in the audience and being pulled left and right with various postdoc offers. And all of my experimental collaborators, one of whom, Matsia Levitas, who's here in the audience, and another one who's instrumental in this work as well, Sanjeevi Sivasankar. And with that, thank you.